Hi students, in this video we are discussing ISRO scientist electronics and communication engineering electromagnetic field theory questions. So in electromagnetic field theory, the syllabus includes in every PSU's even GATE exam also from Maxwell's equations onwards, field theory, wave theory, then after that transmission lines, waveguides, antennas and radars also. Here in October 2025 exam, the questions they asked nearly 8 questions. That 8 questions here I am explaining. The first question is related to waveguides. The question is the wave impedance for a transverse electric mode, which simply TE mode. Here he mentioned what? TE mode. Yes. TE means what? Transverse electric mode in a rectangular waveguide is. So we know that a waveguide is also hollow conducting transmission line, but the difference is it is used in microwave frequency region, whereas transmission lines are used in ordinary frequency region up to kilohertz only. So here all characteristics except this wave impedance is same in transverse electric mode as well as transverse magnetic mode. And we know that the wave impedance, it is the ratio of the magnitude of electric field strength to magnetic field strength. Simply mod E by mod H is known as wave impedance. From that we derived equations also. Eta equals to what? Eta is the wave impedance, that equals to definition mod E by H, electric field strength and magnetic field strength. From the wave parameters, eta equals to j omega mu by sigma plus j omega epsilon. This is the wave impedance equation in a medium. And we know that in free space, the condition is, what is the condition in free space? The condition is sigma equals to 0 and mu equals to mu naught, epsilon equals to epsilon naught. This is the condition in free space. If you substitute the condition here, then eta is become as under root of mu naught by epsilon naught. That equals to, if you substitute mu naught value is 4 pi into 10 power minus 7 Henry per meter, and epsilon naught is equals to 10 power minus 9 by 36 pi farads per meter. We will get in terms of pi means 125 ohms, or in terms of ohms that is 377 ohms, which is a standard value represented as eta naught. Now here excuse me, the question is related to TE as well as TM mode. Here this is the only one characteristic is different in transverse electric mode and transverse magnetic mode, because in transverse electric mode electric field components are perpendicular to the direction of the wave propagation, whereas in transverse magnetic mode magnetic field components are perpendicular to the direction of the wave propagation. If electromagnetic wave is propagating along the plus z direction, in TE, Ez equal to 0, but Hz is not equal to 0, and in TM, Hz equal to 0, Ez is not equal to 0. Therefore, here from boundary condition, eta T equals to eta naught by under root of 1 minus Fc by F whole square. Fc by F whole square. Here Fc is what? Cutoff frequency. Fc is what? Cutoff frequency, and F is operating frequency. F is operating frequency. Therefore, your correct answer is option 2 is the correct answer. Students, the next question. This question is related to antennas. A lambda by 4 monopole antenna radiates 20 watts with a gain of 3 dBi. Here dBi means decibel with respect to isotropic. Then what is its effective isotropic radiated power? This question is related to EIRP. EIRP means what? Effective isotropic radiated power. What is the definition of this effective isotropic radiated power? Means it is the maximum radiated power. It is the maximum radiated power of an antenna in a particular direction. We know that isotropic antenna is an antenna which radiates power equally, uniformly in all directions. But with respect to isotropic antenna, we are calculating the radiated power, transmitted power, directivity, directive gain, power gain of given antennas. So here EIRP means effective isotropic radiated power. Here the meaning of this definition, this term is how much effectively radiates, how much maximum radiated power of given antenna in a particular direction. So here what is the effective isotropic radiated power formula? Means radiated power into gain, radiated power into gain of an antenna. This is the formula. So in our question, radiated power is given as radiated power, I am writing PR, and gain I am writing G. Here radiated power is given as how much? 20 watts, and gain is given 3 decibel dBi with respect to isotropic, in terms of isotropic. But when we are calculating this effective isotropic radiated power, your options are not given in decibel, then you represent this value into non-decibel. So I am writing here, generally gain is represented in terms of power. So I am writing 10 log gain G base 10 is given as what? 3 dB. So then I am writing log G base 10. Log G base 10 equal to what? 3 by 10. Then from here I am applying anti-log both sides. Then G equal to 10 power 3 by 10. That equals to I am writing 10 power 0.3. 10 power 0.3. We know that root 10 approximately 3. Root 10 means what? 10 power 1 by 2. Root 10, that equals to what? 10 power 1 by 2. That equals to 10 power 0.5. That is approximately I am considering 3. So here this is 0.3, this is 0.5, 0.3 less than 0.5. This is approximately I am considering as 2. 10 power 0.3 is approximately how much? 2. Then see here is asking effective isotropic radiated power, that is EIRP. That equals to radiated power is given as 20 watts, and gain in general value, what is that one? 2. So 20 into 2 is what? 40 watts. The answer is 40 watts. Here option 3 is the correct answer. The next question, here we are discussing, this is also related to antennas, and in antennas this question is related to Friis transmission power formula. What is the main importance of this Friis transmission equation? Means by using this equation we can determine received power of receiving antenna. Received power of receiving antenna. Here according to Friis transmission I am considering 2 antennas. This is antenna 1, this is antenna 2. Antenna 1, antenna 2. Here I am considering this antenna 1 is a transmitting antenna. Antenna 1 is transmitting antenna, and antenna 2 is we consider as receiving antenna. Receiving antenna. Right. Transmitting antenna, receiving antenna. This transmitting antenna function transmit the power, and receiving antenna receive the power, and consider the distance between the 2 antennas is D. What is D here? Distance between transmitting antenna and receiving antenna. And you remember here you consider PT. What is PT? Transmitted power. Transmitted power. Similarly PR, received power. transmitted power is PT, PR is received power, and GT, gain of transmitting antenna. What is GT? Gain of transmitting antenna. And GR is gain of receiving antenna. Gain of receiving antenna. GT, gain of transmitting antenna, and GR, gain of receiving antenna. D is the what? Distance between the two antenna. If F is operating frequency, then from F lambda equal to C by F meters. What is lambda? Means wavelength of the signal. What is lambda? Wavelength of the signal. So here PT, transmitted power, PR, received power, GT, gain of transmitting antenna, GR, gain of receiving antenna, D is the distance between two antennas, and lambda is the wavelength of the signal. Then according to Friis transmission formula, PR is equals to PT into GT into GR into lambda by 4 pi d whole square. This is the Friis transmission formula. PR is equals to what? PT into GT into GR into lambda by 4 pi d whole square. What is PT here? Transmitted power. GT is gain of transmitting antenna. GR, gain of receiving antenna. Lambda is the wavelength of the signal, and D is the distance between transmitting antenna and receiving antenna. Now again I am reading the question. According to Friis transmission equation, the received power PR is directly proportional to, is asking PR directly proportional to what? 1. The square of the distance between antenna, it's wrong because it is inversely proportional. And second one is the square of the wavelength. Yes, it is correct. But the square of frequency means again lambda, frequency, both are inversely proportional to each other. So that is inversely proportional. That's why this is also wrong. And the cube of the transmitted power, this is also wrong. So correct answer is, according to Friis transmission equation, the received power is directly proportional to square of the wavelength. Here wavelength means lambda, lambda means wavelength of the signal, where lambda equal to C by F. Option 2 is the correct answer. This is question number 4, and this question is also related to antennas. First I am reading the question. The radiation resistance of an antenna is 63 ohms and the loss resistance is 7 ohms. If antenna has a power gain of 16, then the directivity is. Students, according to efficiency of an antenna, here I am writing in terms of resistance. Efficiency eta. Efficiency of an antenna in terms of resistance, I am writing eta is equals to RR by RR plus RL. RR by RR plus RL. What is RR? Radiation resistance. RR is what? Radiation resistance. Radiation resistance. And what is the value is given here? Radiation resistance is given as 63 ohms. Radiation resistance given as 63 ohms. And RL is loss resistance. Loss resistance. Loss resistance is given as how much? 7 ohms. Radiation resistance is 63 ohms. RL is what? 7 ohms. First I am calculating antenna efficiency. Then antenna efficiency eta equals to 63 by 63 plus 7. That is 63 by 70. 63 by 70. So 7 1 ja 7, 7 9 ja 63. So what is the efficiency value here? 0.9. The efficiency value is 0.9. Then he is asking what? See, if antenna has a power gain of 16, then he is asking directivity. From the definition antenna efficiency, one more definition I am explaining. Eta equal to GP by GD. Eta equal to what? GP by GD means what? It is the ratio of power gain to directive gain. It is the ratio of power gain to directive gain. Here we know that the maximum directive gain is known as what? Directivity. So I am writing the formula here. Maximum directive gain, that is GD max equal to directivity. So eta equal to, I am writing GP by D. Then directivity is asking directivity D equals to GP by eta. GP by eta. What is GP is given? Power gain given as 16 and efficiency just now we calculated, that is 0.9. So that equal to, I am writing 160 by 9. 160 by 9. So 9 1 ja 9, remainder 7, 70, 9 7 ja 63, point again 7, again 7. So 17.77. 17.77 decibel, that is the answer. Here what is the answer? 17.77 decibel. What is that one? Directivity. Option 3 is the correct answer. This is the fifth question in our EMFT theory questions. This question is related to transmission lines. A lossless transmission line is 80 centimeter long and operates at a frequency of 600 megahertz. The parameters are L equals to 0.25 micro Henry per meter and C equal to 100 picofarads per meter. Then the phase velocity is. This is the question. And here we know that condition is given, the transmission line is lossless transmission line. What is the meaning of lossless transmission line? Yes, a transmission line said to be lossless when the conductor of the transmission line is perfect conductor and the dielectric medium between the two conductors is a perfect dielectric. From that definition, when the conductor of the transmission line is a perfect conductor, that means R equal to 0. And when the dielectric medium between the two conductors is a perfect dielectric, then we consider as Z equal to 0. So the condition for lossless transmission line is here R equal to 0 and Z equal to 0. And by using secondary constants, that is characteristic impedance Z0 and propagation constant gamma, here the phase velocity definition is what? Vp is equals to omega by beta. Omega by beta meter per second. Omega, that is angular frequency or angular velocity, and beta is what? Phase shift. Here in lossless transmission line, propagation constant gamma is equals to alpha plus j beta, and that equals to under root of R plus j omega L, R plus j omega L into G plus j omega C. Now the condition for lossless transmission line, R equal to 0 and G equal to 0. When R equal to 0, G equal to 0, then gamma equals to what here? R0, G0, j omega root LC. What is gamma here? J omega root LC. From comparing attenuation constant and phase constant, here alpha is equals to 0 and beta equals to omega root LC. If I substitute this beta value here, then phase velocity Vp equals to, I am writing formula 1 by under root of LC. What is L here? Series inductance, units are Henry per meter, and C is shunt capacitance, units are farads per meter. Now I am substituting the given values here. L is given as 0.25 into 10 power minus 6 micro. And capacitance value is given as 100 pico. 100 into 10 power, pico means what? Minus 12. Then I am writing that equals to 1 by under root of 0.25. I am writing as 25 by 100 into 100, 10 power minus 6 into 10 power minus 12, that is 10 power minus 18. Then 100 cancel, that equals to 1 by under root of 25 into 10 power minus 18. that equals to 1 by root, I am removing, then 1 by 5 into 10 power minus 9. That equals to 10 power 9 by 5. What is 1 by 5? That is a 0.2. 0.2 into 10 power 9 meter per second. That is the answer. Here all values are given in 10 power 8. Therefore, the correct answer is here 2 into 10 power 8 meter per second. What is the answer here? 2 into 10 power 8 meter per second. Here option 2 is the correct answer. This is the question number 6. This question is related to field theory question. And in field theory, this question is related to boundary conditions. First, I am reading the question. A boundary separates two magnetic materials. This is, we are considering as a boundary. A boundary separates two magnetic materials of permeability mu1 and permeability mu2. So, I am considering this is medium 1, this is medium 2. Medium 1 has permeability mu1 and medium 2 has permeability mu2, where units of permeability is what? Henry per meter, and mu equal to mu naught into mu r. Two magnetic field vectors in mu1 is h1 and in mu2 is h2 are given. So, here in medium 1 is given magnetic field vector h1 and is given here h2. Yes, what is h here? Magnetic field intensity. Again I am reading the question. The magnetic field vector in mu1 is h1 with a normal component hn1 and tangential component ht1, while that in mu2 is h2 with a normal component hn2 and a tangential component ht2. Then the derived condition would be yes. So students, in field theory, the main importance of this boundary condition is to determine the field component of one medium if we know the field component of in another medium. And here the field components are vector components which consist magnitude as well as direction. According to the properties of this vector decomposition, any vector can be decomposed into two components. One is a tangential component, another is the normal component. What is the meaning of tangential component here? A tangential component is a field component which is parallel to the boundary line, and normal component is the field component which is the perpendicular to the boundary line. So, according to the decomposition concept, here H1 is the magnetic field vector in medium 1 is decomposed into two components. One is HT1 plus HN1. HT1 plus HN1. What is HT1? Tangential component of magnetic field intensity in medium 1, and HN1 is normal component of magnetic field intensity in medium 1. Similarly, in medium 2, the magnetic field intensity component is H2. Again, from decomposition concept, where H2 is equals to what? HT2 plus HN2. And similarly, like HT1, what is HT2 here? The tangential component of magnetic field intensity in medium 2, and HN2 is normal component of magnetic field intensity in medium 2. And from Maxwell's equations in integral form, by using closed loop line integral of H dot dl equals to I, and law of conservation of magnetic flux, surface integral of B dot ds equal to 0. From these two equations, here two derivations we derived. One is HT1 minus HT2 is equals to K. This is the derivation which is related to tangential components in medium 1 and medium 2. Here HT1 is what? Tangential component of magnetic field intensity in medium 1. HT2 is a tangential component of magnetic field component in medium 2, and K is the surface current density. If K equal to 0, then what is the condition here? HT1 is equals to HT2. This is the two relation. If K is not equal to 0, then the tangential components of magnetic field intensity are not vanishes. If k equal to 0, the tangential components of magnetic field components are vanishes. This is the relation in terms of tangential components. Similarly, using normal components, law of conservation of magnetic flux, Bn1 is equals to Bn2. That means what? Bn1 equals to Bn2 means normal components of magnetic flux density in medium 1 and medium 2 are same. Bn1 equals to Bn2. And from the relation B equal to mu h, I am writing here mu1 into Hn1 is equals to mu2 into Hn2. Mu1 into Hn1 is equals to mu2 into Hn2. So these two are relation in terms of tangential component. These two are relation in terms of normal components. These are the four equations. Now I am using this four equation. See, H1 equal to H2 and HT1 equal to HT2. Wrong, because H1 not equal to H2. And second equation is HT1 equal to HT2 and mu1 Hn1 equals to mu2 Hn2. Yes, this is correct. H1 equal to H2, that is wrong, and mu1 Hn1 equal to mu2 into Hn2. Second condition correct, but first condition wrong, like same option 1. H1 equal to H2, HT1 equal to HT2 and mu1 Hn1 equal to mu2 into Hn2. Here this condition correct, but H1 is not equal to H2. That's why here option 2 only correct. Why H1 is not equal to H2? Because just now I explained here, H1 is the magnetic field component in medium 1. H2 is the magnetic field component in medium 2. Here HT1 equal to HT2, but Hn1 is not equal to Hn2. That's why H1 is not equal to H2. So option 2 is the correct answer. This question is also related to field theory and electromagnetic wave characteristics. This question is related to loss tangent. So what is the importance of loss tangent? Means by using loss tangent we can determine the type of the medium. If the medium is a perfect conductor or a good conductor, if the medium is a good dielectric or a perfect dielectric, everything will be decided by loss tangent. Here this loss tangent is known as what? Tan theta. Loss tangent is what? Tan theta. What is the definition of this tan theta? Loss tangent means it is the ratio of magnitude of conduction current density to displacement current density. Tan theta equals to what? Mod JC by JD. Mod magnitude, because JC, JD are vectors. So magnitude of JC conduction current density, JD displacement current density. And what is conduction current density formula? JC equal to sigma E, where sigma is conductivity, E is the electric field intensity, and JD equal to displacement current density, and JD equal to dou D by dou T, again D equal to epsilon E. Conduction current density we are considering in conducting medium, and displacement current density we are considering in dielectric medium. That's why by using this loss tangent we can decide the medium whether it is a good conductor or a good dielectric. If you substitute the two formulas here, JC equal to sigma E and JD equal to dou D by dou T and D equal to epsilon E, tan theta definition is sigma by omega epsilon. This is the definition of loss tangent. And here he given one more definition in terms of permittivity. This is real term of permittivity, epsilon prime and epsilon double prime, that is the imaginary term of permittivity. From that, loss tangent definition is given as what? Imaginary term of relative permittivity to real term of relative permittivity. This is the definition. So here is given one condition, if tan theta tends to infinity, if tan theta tends to infinity, that means the value is very, very large value. The value is very, very large value. Now I am substituting this condition in our equation. That means sigma by omega epsilon is very large value. That means sigma is very greater than omega epsilon. That means the medium is a perfect conductor. Remember, the medium is a perfect conductor when means the last tangent tan theta is very large, tan theta tends to infinity, sigma is very greater than omega epsilon, or sigma by omega epsilon is very greater than 1. All these conditions are correct. Similarly, when the medium is a perfect dielectric means if tan theta tends to 0, or if sigma is very lesser than omega epsilon, or sigma by omega epsilon is very lesser than 1. So, by using last tangent, we can decide the medium is whether it is a perfect conductor or perfect dielectric. If the value is large means good conductor, if the value is less means good dielectric also we are deciding. So, here is mentioned tan theta tends to infinity. That means the medium behaves like a perfect conductor. That's all. Option 1 is the correct answer. And option 3, insulator, that is wrong. And it gives the displacement current, dominates conduction current, that is also correct. But that is when it is tends to infinity means it is only perfect conductor. Option 1 is the correct answer. Yes, students, this question is also related to transmission lines in field theory ISRO question paper. A 1 wavelength long 50 ohms transmission line is terminated in ZL equal to 30 minus J40 ohms. Its input terminals are connected to the load end of a 100 ohms quarter wavelength line. Then what is the impedance seen at the input to the 100 ohms transmission line? This is the question, and is asking the impedance of the quarter wavelength transmission line. When a length of the transmission line, when the length of the transmission line is a lambda by 4, then it is a quarter wavelength transmission line. Is given as here the characteristic impedance of this quarter wavelength transmission line is given as 100 ohms. And the terminated load impedance is also given here. What is the value is given here? That is 30 minus J40 ohms is given. 30 minus J40 ohms is given. Then is asking the impedance at the input. That means indirectly is asking what? Input impedance of this quarter wavelength transmission line. Then what is the input impedance of this quarter wavelength transmission line? Z input equals to Z0 square by ZR, where Z0 is characteristic impedance of this lambda by 4 transmission line, and ZR is the receiving end impedance or load impedance or terminating impedance. Here in our question, Z0 is given as how much? 100 ohms, and ZR is given as 30 minus J40 ohms. This is the data given. Is asking the input impedance of this lambda by 4 transmission line, students. So I am writing here Z input equals to Z0, that is 100 into 100 divided by 30 minus J40. Now I am rationalizing because denominator is a complex number. 100 into 100 as it is I am writing 100 into 100, rationalizing. That means 30 plus J40 numerator. In denominator 30 minus J40 into 30 plus J40, A plus JB into A minus JB become as A square plus B square. 30 square means what? 900. 40 square means what? 1600. So that equals to I am writing 100 into 100 into 30 plus J40 and divided by 2500. 1600 plus 900, 2500, 2 zeros cancelling, 25 1 ja, 25 4 ja, here 100. So 4 into 30 plus J40. That equals to 430, how much? 30 into 4, that is 120, plus 40 into 4 is 160. 120 plus J160 ohms is the answer. 120 plus J160 ohms is the answer. Option 3 is the correct answer. Thank you, students.